Video, we're going to take a look at a recent assessment we've done on both the thermal physics part of the course and also on SHM, with a bit of mechanics from the lower sixth thrown in too. So the first thing we've got here, the first question says the pressure of an ideal gas is inversely proportional to its volume, and that is an incomplete statement of Boyles' law. What two conditions are necessary to complete the statement of Boyles' law? So I'm going to use the equation of state, PV equals NKT, to explain this. So we know that PV is equal to NKT. So if we want to make PV equal to a constant, or essentially pressure inversely proportional to volume, we can see from the equation that we need to keep temperature the same, and we need to keep the number of molecules or the number of moles of gas the same as well. And you do need to be that specific. If you say some vague stuff like the amount of gas or something like that, that's not specific enough. It needs to be specifically the number of molecules or moles of gas. For this question, I saw a lot of people saying things like no intermolecular forces, elastic collisions, all of these different things that have cropped up as part of the thermal physics course. These are not what this question is looking for at all. So these two things we can see up here we would call conditions. So pressure, volume, temperature, they're all conditions in which a gas can find itself. These are all from another part. These are the assumptions we make when we're dealing with ideal gases using the kinetic model of matter. So it wanted the conditions here, so it's wanting temperature and number of molecules. Okay, so the next, we've got a variable volume container, maybe it's a piston or just a cylinder, and we've got some values for the volume and pressure and temperature to start with, and it also tells us that in these conditions that the volume of 1 mole is 0.024 meters cubed. And what we're going to do is we're going to heat it and compress the piston, so we change temperature and volume. And we've been given some final conditions, so we know the final temperature and we know the final pressure. And we're going to deal with the idea that 1 mole of gas has a mass of 0.029, which is around what it is for air. So that's all the information. The first thing I'm going to do is I'm going to pull out all the data we've been given. There's a lot of text there. Let's first pull out the key information. So we've got volumes, pressures, and temperatures there. So we've pulled those out. And the next thing to note is it says we've got air trapped in a container. So what I'm taking that to mean is it's the same as using the word sealed. We've got a constant number of molecules or number of moles of gas there. So that's what I'm taking from that. So if we now have a look at the question, so what we want to do is actually find the volume of it occupies at the final stage. So one of the things people I've seen tried for this question to find the volume was by using Boyle-Charles or pressure laws. So you can't use those because neither like pressure or temperature or volume is staying the same. So those would not be appropriate ways. But we do know that the number of molecules of gas is constant. So we can apply the condition you can see at the bottom, and you can rearrange it to make the final volume the subject, because that's what we're trying to calculate here to start with. So the reason I've laid it out like that is we're going to see lots of the powers of 10 end up cancelling each other out. So once we substitute the numbers in, the reason I haven't put times 10 to the 5 in is because you'll notice both the pressures have that, so the 10 to the 5s cancel out. So laying it out like this allows you to spot cancelling things quicker and make it easier to calculate. Now, if we type those numbers into our calculator and give an answer to an appropriate number of significant figures, it gives us a final volume of 4.4 times 10 to the minus 4 meters cubed there. So the next to do is work out the number of moles of air in the cylinder. So one way we could have done that is applying the ideal gas equation. Now we know P, V, T, and R. That would be one way. Another way we can do is use these values that has been given to us. So it says under the initial conditions, 1 mole is 0.024 meters cubed. We know to start with we had 0.01016 meters cubed. So what that's going to allow us to do is have another way of calculating the moles. So at a fixed temperature and pressure, the volume of a gas is directly proportional to the number of molecules. That's essentially what this expression is a statement of. So we know 1 mole, so I'm making N1 1 mole, has a volume of 0.024. So then how many moles would have a volume of 0.016 is essentially what I'm doing. And that gives a value of 0.067 moles. But like I said, if you wanted to, you could have used the ideal gas equation to solve this as well. It would give you the same answer. Okay, so that's the number of moles. So we want now going to calculate the density. So we're going to need to work out what the mass is. So we know what the initial volume is. We're going to need that later on. And we know how many moles there are. And I realize there's a 0 gone missing from that statement there. So in all circumstances, the mass is directly proportional to the number of moles that we've got there, because essentially number of moles and mass are both measures of the quantity of stuff we've got. So if we know 1 mole has a mass of 0.029 kilograms, we want to figure out what the mass of 0.0666 moles is. So when we plug those numbers in, we end up with a mass of 0.00193 kilograms there. So again, as I said to you, we're just using the fact that mass and number of moles are directly proportional. Now we've got the mass, we can figure out what the density is because we know the volume as well. And it comes out as 1.2 kilograms per meter cubed. And given that this is air, that should not be surprising to you. That is a very common figure that you see. So it's well worth knowing what the density of air is because you will often get asked to calculate it. Okay, so that's density. So the next part wants us to state and then explain what happens to the speed of molecules in a gas as the temperature increases. So this question is essentially asking you about this graph. So this graph illustrates what is happening inside a gas at different temperatures. So the peaks we can see there are known as the RMS speed, or sometimes the average molecular speed. So you can see that any temperature, gas particles have a range of speeds, but the RMS speed changes as we change the temperature. So in terms of what's happening when we heat something, so thermal energy is being transferred to increase the internal energy of the gas. That's the energy exchange going on. And we know that internal energy is directly proportional to the temperature there. So as temperature increases, we know internal energy is increasing. So that's what's happening. So the impact of that is that, as we can see from the graph, if we increase temperature, the RMS speed of a gas is increased. And we could use some of the equations to illustrate this. So hopefully you've seen things like the internal energy is 3/2 nKT, for example. And also that would be the sum of all the kinetic energy. So we can use that too. But essentially this question's asking you about this graph. And it's important that we understand what's going on with this graph, because in the astrophysics part of the course, you come across something called Wien's displacement law, where you start seeing very similar graphs appearing with light from stars. So this distribution is something that crops up everywhere when we're modeling whole systems in physics. So it's important you get a good understanding of it. So quite a common thing that came up with this question is people just say things like the speed of the molecules increases. That is not an accurate statement, because what can happen is some of them, maybe their speed doesn't change. Some of them during the time it heats, their speed will actually decrease. The key is it's the root mean square speed that changes, not just speed there. So you can see that as part of my answer here. So that finishes this first question looking at applying the different gas laws. The next question we're looking at how we can figure out what absolute zero is. What experiment can we do to actually show that absolute zero is minus 273 degrees centigrade, which we now call 0 Kelvin, of course. So there are two possible ways of doing this. So we could keep volume constant and plot a graph of temperature against pressure, or we could keep pressure constant and plot a graph of volume against temperature. But either way, we would need a sealed container so we have a fixed number of moles of gas there. So those are our two options. Personally, I would go for a fixed volume container. It's much more straightforward to get hold of one for a start, and also then you don't have to deal with needing various different size spaces and that kind of thing. So I would generally choose the fixed volume method, and then using a pressure gauge as a way of measuring the pressure and a water bath as a way of measuring or changing the temperature in a controlled way, because we need to ensure that all of the gas is at the same temperature there, and a way of doing that would be to use a water bath. So essentially what I've done here is I've addressed this first bullet point here. We talked about the things we're keeping constant and actually the process we're going to use to do the experiment. So next, let's address the measurements that we're going to take in. So I said we're going to use a water bath, so I'm going to start the experiment at 30 degrees. Water baths obviously can't go below room temperature because they are just heaters essentially. So I'm going to go to 30 degrees, which is above room temperature, and leave it for a period of time to ensure the gas in the container has reached the same temperature there and that the temperature is uniform throughout the whole gas. So that will be part of my procedure. And then I'm going to record the temperature and pressure, obviously a thermometer for temperature, a pressure gauge for measuring pressure. And then what I'm going to do is I'm going to go up in 10-degree intervals up to about 90 degrees C is typically what a water bath can go up to, and getting pressure and temperature values at each of those. So there what we've done is we've talked about the measurements we're going to take there. So next, look at how we'd actually go about finding absolute zero. So we've got pressure and temperature readings, so I'd plot a graph of pressure against temperature, and the temperature is going to be in Kelvin, so I'm going to add 273 to all of my temperature readings there. So then what I'm going to do is I'm going to draw a line of best fit because my data should pretty much be on a straight line, and we're looking for where it intersects with the x-axis because that's the point at which pressure is zero, so that would give us our minimum possible temperature there, or absolute zero. So that's what we would do with our results to find absolute zero. And in terms of justifying why the value obtained is absolute zero, so using our theory of ideal gases, when the particles have minimum possible energy, they're going to have the minimum possible pressure, which is zero. You won't be able to have negative pressure. So therefore, when the pressure is zero, that will be the minimum possible energy of our particles, and therefore that will be minimum temperature, or absolute zero there. And we finished off explaining how we can do this. So the one thing I'll say about this question at this point is, if you get this question in the real exam, they are being very, very nice to you. Pretty much every textbook on thermal physics will tell you exactly step by step how to do this. So this question really is a test of whether you have read the physics textbook and committed it to memory or not. So this would be a very nice longer answer question if you get it. Don't expect them to be as nice to you in the real thing though. So let's now do some and stuff with our kinetic model. So the next question wants us to state two assumptions about the movement of molecules in order to get this equation, which was very nice of them because I already had this earlier. So this is where these things all become relevant. These are the assumptions we are making when we model a gas using the kinetic model and generate our equation PV equals 1/3 nm mean square speed. So these are the things we could have. Obviously, you only need two. Be very careful with these questions, though, because if you write something, you write all of these correct ones and write something wrong, you will start losing marks. Okay, so just be careful. If it asks for two, give two, but any of these would have been completely appropriate. So the next question actually wants us to work out what the mean square speed is. So the first stage in terms of being able to do this is you actually have to know what mean square speed is, which this test illustrated. A lot of people don't and haven't committed this definition to their memory. So mean square speed is just the average of the squares of the speeds. I mean, it's exactly what it says. So what we're going to do is we're going to calculate the average of the squares of the speed. So we square each of the speeds, add them together, divide by the number, which is 3, and that gives us a mean square speed, which would have the units of meter squared s to the minus 2, because it's speed squared. Easy. Okay, so then last part of this question wants us to work out the temperature if we know the average molecular kinetic energy of an ideal gas. So you should know that the average molecular kinetic energy is calculated using 3/2 kT. That's what all of these assumptions were about, getting us to this equation. So if we rearrange it to make T the subject, put our values in, we get a temperature of 3.2 times 10 to the 2, and it's going to be in Kelvin because the temperature in this equation is in Kelvin there. Okay, so let's finish off thermal physics by having a look at a specific heat capacity question. So we've got a bicycle and rider with their mass, and we've got the speed, and it wants us to calculate kinetic energy of the two. This is basically have lots of free marks, enjoy that, so not going to waste any time looking at that. So then the next part, we want the maximum temperature rise in the break blocks if 60% of the kinetic energy is transferred to the block. So to get maximum temperature rise, what would that mean is that all the thermal energy transferred is converted into kinetic energy in the atoms. That's essentially what we're saying. So that's what this equation's for. It works out the temperature change and therefore the kinetic energy change when you apply thermal energy. So that's what we've done there, and rearranged it to get the temperature change there, which we'd express as 13 Kelvin or degrees Celsius. That's fine too. So then what it wants to know is, what assumption have we made? Well, I already looked at that briefly. So we assumed all the thermal energy supplied to the block is used to transfer into kinetic energy, and that none of it is transferred to the surroundings there. So that will be the assumption that we are making. Okay, so that finishes off the thermal physics. Let's have a look at the SHM. So we've got a mass spring system in vertical simple harmonic motion, and it wants to know the two types of potential energy. Pretty easy to start off with: elastic potential energy and gravitational potential energy. A few people for some reason wrote kinetic energy here, which is worrying because you haven't read the question, but pretty much that was fine. And the next question wants the energy changes during one complete oscillation. That costs a lot of people because they didn't read it carefully. And when the mass starts at its lowest point. So at its lowest point, you have got all of the energy in the form of elastic potential energy there. So this is when the spring is stretched out when you've pulled it down. And then when you release it, that's initially transferred into kinetic energy as it moves upwards, and then finally into gravitational potential energy when it reaches its highest point. But so far, we have only answered half the question because it says during one complete oscillation. So we would have to describe the reverse energy transfer back to kinetic energy and back to elastic potential energy to complete our answer here. Okay, so that's energy transfer. Now we're going to look at this in so on this graph you can see we've got total potential energy, so sum of elastic potential energy and GP essentially, and it wants us to identify the time period. So lots of people wrote 0.4 for this because they didn't think about it. So during a full oscillation, we have 2 points at which the potential energy is maximized. So we need to find the distance from the start to the second peak to give us our time period, which would be 0.8 in this example here. You have to think very carefully when you're dealing with energy in SHM. Then, having picked up the time period is 0.8. What we now have to do is sketch a graph of the acceleration against time, and the bit I need to draw your attention to is these two, starting at the highest point and using downward acceleration as negative. So if it's at its highest maximum point, it's going to start moving downwards, which means its acceleration is downwards. So its acceleration must be negative initially. That's the first thing. And then it also is going to have to be at its maximum initially as well, because at your maximum displacement, your acceleration is maximum too. That's one of the conditions of SHM. So we must start at a maximum, and it must be the negative maximum there. So that means we're drawing a minus cosine graph, and we know the time period is 0.8, so we just draw a minus cosine graph with time period of 0.8 there. It is a little bit tricky to do that in PowerPoint. That's pretty much the best I can do at the moment, but that's what we were looking for this question. Okay, so the next question is, we've got the object's mass, and we want to get the spring constant. So the first thing to realize is we also have the time period, because we've just found that out. And if we know the mass, that allows us to use this equation and rearrange to make k the subject, calculate our answer, and give it with the unit of newtons per meter, because it's a spring constant. That is the unit of newtons per meter. I saw one person give this as kilograms s to the minus 2, which I accepted because it's correct, but this is conventionally what we give a spring constant as. So the final part of this wants us to work out the amplitude of the oscillations if we know its maximum kinetic energy. So the first thing is, when it's at maximum kinetic energy, that means all of its energy is in the form of kinetic energy. So we can essentially write an expression that Vmax squared times mass times half would give us the max kinetic energy. You should also know that this equation here is the equation for the velocity of an object in SHM. And this comes from taking the derivative of the displacement equation, which is written normally in either of these two forms. If we take the derivative, we get this expression here, and that means the maximum would just be 2 pi a over t, because this function is going to be maximized when our sine function is equal to 1 or equal to minus 1. Either it doesn't change anything because we're doing energy. So now we've got an expression for Vmax. We can substitute that into our kinetic energy equation, rearrange to make the amplitude the subject, put the numbers in and calculate our answer. So the actual answer comes out as 43, but that's pretty much 40 millimeters. So we've shown what we need to there. Okay, so that finishes this question. We're going to look at a different circumstance of SHM. So we're going to look at a swing oscillation. So we've got the mass of the two objects, which we'll add together to give the mass of our system. And when it's pushed, the swing reaches a vertical height of 0.5 meters above its rest position. So its change in height is half a meter. And we want to show that the maximum gain in GPE is about 88 joules using G equals 9.8. So using some lower six mechanics, we should know that change in GPE is mg delta h. So we add the two masses together, times 9.8 times half a meter gives us 88.2, which is pretty much 88 joules. The next part says the work done against resistive forces is 20 joules. How much work must the boy have done? So essentially what this is thinking about is now applying conservation of energy. So if your energy changes, some work must have been done on you, because at the maximum position the kinetic energy is 0, so we don't have to worry about a change in kinetic energy. So the net work done will be the difference between the resistive work done and the boy's work done, which you can see there. So if we rearrange that, we can see the work done is 108 joules. So the reason the 20 is negative is because air resistance does work to decrease the energy of the system, whereas the boy is doing work to increase it, so that's a positive number. So once he's pushed it, it says during the push, he's in contact for a distance of 0.4 meters. Calculate the average force. So we know the work done and we know the distance, and you should also know that work done is the average force times the distance in the direction of the force. So we can put those numbers in and that will give us our average force. So once we're at the maximum point, obviously you would come back, and we want to work out the speed which you pass through the equilibrium position, or the lowest point, but we've still got the same resistive force. So again, we're going to be using conservation of energy, but this time we're going to have changes in GPE and kinetic energy. What we need to do next is rearrange that, because we want the speed, so we want the change in kinetic energy. So the initial speed is 0 at maximum displacement. We know the change in height is ½ meter downwards. And we know the work done by air resistance would be minus 20 joules, because it's always opposite to the motion or the velocity. So we can rearrange our expression to give us velocity, substitute our values in, and that comes out as 2.8 meters per second there. One of the most common ways people went wrong with this is they just completely ignored the work done against resistive forces and got themselves 0 for this question because they weren't paying attention. But you have to make sure you factor it in as well. And the last for this question wants us to sketch how the kinetic energy changes over 2 complete cycles of motion, starting from the maximum displacement position. So there's a few key things our graph needs to show. It needs to show that initially kinetic energy is 0 because you're at maximum displacement, and therefore after 2 oscillations it would finish at 0. We should have 4 max kinetic energies because there's 2 per cycle, and because there's work being done by resistive forces, the total energy should be decreasing and therefore the kinetic energy should be decreasing. So that's what I should be looking at a graph of. And a key thing to show on your graph is that the time period should stay constant, because damping forces don't affect the time period, they just affect the amplitude of it. Okay, so that finishes the questions on SHM. Next, we're going to look at some motion, energy and power, which is the last question on this test. So the first thing we want to do is we want to determine the distance traveled from a velocity versus time graph in 10 seconds. So I saw lots of people doing this. They used S equals U plus V over 2 times T and got completely the wrong answer, because you cannot use this equation in this scenario. You can see from the graph the gradient changes during the motion, therefore the acceleration changes during the motion, therefore you are not allowed to use SUVAT equations. What we have to do is work out the area under the graph, which you can see I've done by splitting it into 3 shapes, because we want to be as close as we can to the actual graph, and then worked out the area of those shapes and got an answer of 432. You allowed anywhere between 420 and 440, I believe, for this question. So there is a range, but you have to be pretty close. The next question wants us to show the instantaneous acceleration is about 4 meters per second at 10 seconds. So to find instantaneous acceleration, if we knew the equation, we could find the derivative, but we don't, so we have to draw a tangent to the graph at 10 seconds. Then we have to find the gradient of that tangent, which I found and got about 3.57, which isn't exactly 4, but it's in the right ballpark, so we know we've done it right there. Okay, so we've got acceleration. So it wants us to find the magnitude of the resistive force at 10 seconds. So you should know that the resultant force would be equal to the mass times the acceleration if mass is constant, and the resulting force will be the difference between the driving force and the resistance force. So if we want to find the resistance force, we just have to rearrange it, substitute in our values for mass, acceleration, and driving force, and that will give us our resistive force of 3.2 times 10 to the 3 newtons. So the last calculation wants us to work out the power of the car at maximum speed. So if we want to know the power, we need to know the force applied by the car and multiply it by the maximum speed. So from the graph, the maximum speed is about 89. Our force from our engine is 5,800, giving us a power of 5.2 times 10 to the 3 kilowatts, because that's the unit it wants it in. Okay, so the last question is a context explain type question. So we're talking about DRS, which those of you who follow Formula One will know is a way of reducing drag to give you higher speed. So some keys to pull out here. So the aim of the device, DRS device, is to decrease drag. So we're going to use that. And what we're trying to do is essentially compare when DRS is not used to when it is used. And first thing we're going to do is explain the shape of the graph we've got already, and then we'll explain how a DRS graph is different. So Let's start with explaining the graph we have. So I've essentially broken it into 3 sections there. So the first section, it's a straight line graph to start with. And the reason for that is because at small speeds, drag force is negligible. So the resultant force is equal to the driving force, so it's constant. And if the resultant force is constant, we know the acceleration, and therefore the gradient of the graph will be constant, so it will be a straight line. That's the first section of the graph. The next section of the graph, we can see the gradient is decreasing. So the reason for that is drag force increases as speed increases, so the resultant force decreases, causing the acceleration to decrease. That's why the gradient decreases. And eventually the gradient becomes 0 because drag force is equal to the driving force, resultant force is 0, and therefore the acceleration is 0. So that fully explains how the velocity changes from the graph. So we've done this part of the question. The final part will be explaining how the graph is different if we use DRS. The first part of it would not change at all because air resistance is still negligible, so we're still going to have a constant gradient, so we're still going to have a constant acceleration. So the first part isn't going to change. The second part will end up with a steeper gradient because drag force is smaller, therefore resultant force is bigger, therefore acceleration is bigger. So it would go above the line, if you like. And what would happen is it would reach its terminal speed at a higher speed because it would have to be traveling faster for the drag force to equal the driving force. So it'll have a higher top speed, and those would be our differences there, and that's us explaining it there too. Okay, so that finishes this exam paper on thermal physics, SHM, and some mechanics. If you have any questions about any of those different parts, please do feel free to comment and ask. I'm more than happy to answer those for you. But I hope this has been useful for you. Thank you very much for taking the time to watch.